Okay, great. So yeah, I already introed myself. I'm Tyler for people just walking in, but interest of time, we'll get going. Cool, so our agenda here, I'm gonna outline some terminology just to make sure we all know what I'm talking about. Then we'll talk about why we care about these at all in the first place. And then I'm gonna discuss a couple different structures in different categories like lists, streams, queues, trees, and zippers. So what are purely functional data structures? Wikipedia says a purely functional data structure is a data structure that can be implemented in a purely functional language. This is 100% correct and 100% useless. So what we really mean by that is they have two primary properties. They're immutable, which means we don't do any destructive updates. If we want to make a change, we actually make a new structure. And generally, they're expected to be persistent, which means that when, say, we make that modification, we go ahead and keep both of them around in the runtime. So if we have a list and we add a new head to it, the old list still exists, and anything that had a pointer to that old list is still able to use that, and it still works fine. So pretty much all functional programming languages rely on the garbage collector to ultimately clean these up when nothing points to them anymore. A little more on persistence. There's some cool benefits here. Because we don't destroy the old structures, you could actually think like you could maintain a list of all previous versions of your structure. And in fact, some libraries like the popular JavaScript library Redux that people often use with React does this exact thing to implement what's called time travel debugging. So you can actually there's a way to debug your programs where you can actually see what the state of your program was from the time it started, like every change all the way up to the present. So it can be really useful for that question that often happens, especially in front-end apps, I think, where you're like, how did I get here? Like the state is in some weird state. I have no idea how. This doesn't make sense. Well, with a feature like this, you can actually trace it back from the step one. It's very useful. Okay. So other reasons why we care, I would say the biggest reason that they're finding a lot of prevalence is concurrency. Moore's law is kind of giving way, and more apps are moving towards concurrent models. You see non-blocking everywhere, different thread models, Go, like CSP, things like that. And it turns out that purely functional data structures, because we don't mutate, we just make new versions, actually work perfectly in these environments. Like if you have other threads referencing the old one, it doesn't matter. This thread can make a new one. You just don't have to deal with locks. You don't have to deal with these issues. And another reason, kind of going back to our definition earlier, if you're using like Haskell, you just kind of have to. You don't really have a choice. And third, if you've used anything like Apache Spark or things like that that sort of pretend there's a data structure over some distributed data, like an RDD, they model those as functional data structures. In some sense, like under the hood, there might be some funny business going on, but like if you've used RDDs in Spark, you map, you get a new RDD. You can't mutate a specific RDD. So these are actually showing up in a lot of situations like that. All right, so let's start with the basics. A list is kind of the easiest example, and this is some Scala code, and in all these examples, I kind of ignore like error handling and things just to keep the amount of code on the screen succinct. So yes, like there's no bounds checking or anything like that. If you're not familiar with Scala, basically a trait is similar to an interface in a lot of other languages, and then I have two members of that list. So basically a list is either an empty list, which I represent as this object nil, or a cons cell, which is sort of an old term from the Lisp days, which has one element and a pointer to another list. So basically what will happen is every list ends with a nil, and then you build up conses in front of it, and that makes your linked list. So yeah, cons is just the operation that creates a new one, and I put an append function here because I think one thing that's interesting is if you want to make a new list by putting one on the end, what you actually do is you kind of iterate through the first list to the end, and then you actually just make a new cell that points to that old list and kind of build up on top of that. So that the second list, like list BS in this case, actually is reused wholesale in the new list we've constructed. I actually have a diagram of that. So this would be like a traditional imperative way to do a linked list append. We actually have this list XS. We would go into it when we make ZS, and we would actually change this 2 cell directly to point to 3. The problem with that is that in a concurrent environment, like if there's still references to XS, they're now going to have this whole list. Like XS has been changed. This is efficient, but it destroys XS. In a functional language, we actually make this new list ZS, we leave XS alone, and we just end up pointing, we copy all the elements of XS, but have the last one point to YS. So in this case, YS is reused in ZS, but is also left alone, and XS still exists. So this pattern you'll see everywhere. And this is one of the reasons that why in a single example, it seems like these structures are really wasteful. It's like, you're doing all this copying, why don't you just change this pointer? But in practice, in an actual production program where you have structure reuse, the memory isn't necessarily as bad as it seems because of the fact that you can reuse partial structures. So lists are cool. They're ubiquitous. Every language has one. They're easy to implement. And they're good for things where you're just going over the whole thing, like doing maps and things like that. And you can represent a stack trivially from a list. But it turns out they're not great for a lot of things. Random access is really bad because you always have to iterate from the front to get to wherever you're at. And appending in this example is always going to take the cost of your first list. So if you have a big first list and you want to add even just one element on the end, you have to go through the entire first list, recreate it, and it's very slow. So this next one doesn't necessarily deal with all these issues immediately, but we're going to kind of build on that. So one modification we can do on a list is make it a stream, otherwise known as a lazy list. And it's basically just a linked list where we delay the evaluation of the next cell till we actually need it. And in Haskell, because the runtime is actually lazy by default, a list is effectively a lazy list or a stream. Also, one clarification, sometimes stream is used to reference other things, like stream processing, like storm. There's just kind of some different definitions. Here I'm just meaning like a lazy linked list. So in Scala, we have a concept of by name parameters, which is represented by, well, actually we don't use it here. These are just functions with no arguments. You can kind of call them thunks. So you wrap something in a function to delay its evaluation until you actually call that function. So the stream is very similar to the list, except that we sort of delay the execution of this tail. Here, if we just have, without the parentheses, if we just have this also is a Scala syntax thing where it won't evaluate this till the first reference. So if I was to pass in like to this method, like 2 + 2, for example, it doesn't actually, in most languages or in call by value function application, the 2 by 2 would happen first, then 4 would get passed in. This way, it actually passes in the like computation 2 + 2, and it won't actually happen until someone references BS. So, an interesting thing about append in this case, because of this lazy evaluation, we can immediately return from the operation. Like we say we want this stream and this stream added together, it will immediately return like without doing any work. And it won't actually do the work of appending until you like have iterated over the list till you get to the second one. So it kind of saves that computation until later. And this plays an important role a little further on. So one thing to note about streams in general is that if the way I implemented it previously, if you were to have an expensive operation in your like head, for example, every time you reference that, like h1 and h2 both reference x.head, it would be recomputed in each time. So this is often not desirable. In Scala, we have a way to actually tell the runtime we want to like basically memoize or cache that value once it's referenced. So by actually declaring these lazy vals here, what Scala's runtime will do is when those are accessed, when it actually gets, the computation is forced, it will actually kind of behind the scenes turn that into just a direct reference to the value instead of a lazy reference, so that if we were to be using this cons up there, the second reference to x.head would actually be immediate and wouldn't recompute. In functional programming, this is great because there's no side effects in there. If you had side effects like log messages hidden in that computation, this does become like non-transparent because you don't know how many times exactly this will run. It doesn't necessarily log every time it runs. So a thing to keep in mind. Oh yeah, just a quick thing that's cool with streams. Because they're lazy, you can actually use a technique called co-recursion to actually build you can make infinite streams that reference themselves. So here we have ones that conses or adds one onto itself, which seems kind of crazy, but it's because the tail application is delayed until it's needed, and by the time it's needed, it exists. And it already had one in the front. The reason this is co-recursion versus recursion, just terminology note, recursion starts at a top case and kind of descends down to a base case, and that's where it terminates. Co-recursion starts from a base and builds out through the recursion. So the co-recursion never ends, it actually goes forever. But yeah, you can use these streams, like that's an actual working Fibonacci implementation that will just like create the stream of Fibonacci numbers in a few lines. Okay, queues. So in imperative programming, a queue is generally just like an array list or something in the back, and you just keep appending to the end of the list instead of the front. And if you need more space, you expand it. That's kind of the usual way. But we can't really do that in a functional queue because if we're backing it by a list, for example, as we talked about earlier, adding to the end of the list is really expensive. So how do we do it? Well, there's actually a technique that, funny enough, I first encountered in a interview question is make a queue from 2 stacks. It turns out this is actually the way that this is done. In fact, the Scala queue, immutable queue, actually uses this exact method. You keep 2 lists instead of 1, and whenever an enqueue operation happens, you append to the rear list, and whenever a dequeue operation happens, you pull the head of the front list. So, as you might guess, somehow we need at some point to move things from the rear to the front. And here's a Scala implementation of a queue. And most of the work happens in this migrate function, as you can see. Basically what happens is every time this gets called on enqueue and tail, which is effectively, if you were to make a dequeue, I didn't put it on here, it would return a tuple of the head and the tail because you can't mutate. So you basically would say, here's the element you wanted in the new queue. So you could wrap that. But when you want the tail, if the front list, basically you just pull from the front list as long as anything is in there. And once you run out, what you do is you actually take the rear list, you reverse it, move it to the front, and then put an empty list in the back. The reason you have to reverse it is because basically you have a stack in the back, and by reversing it, it becomes a queue. So, yep.
Do you know if in Scala it's multi-thread or thread safe?
This is thread safe.
Well,
because you always get the immutable queue. Because you get a new queue out to use for other operations, like it is actually thread safe. Wouldn't be mutated, like nothing's mutated. The mutable queue, I'm sure, is implemented completely differently and may not be thread safe. I don't actually know. Did that? Okay. Okay, so one thing, you sort of expect a queue to have a runtime of like 01 for the operations. And other than, yeah. So one technique we have to do when dealing with actually both imperative and functional data structures, but I think it comes up a lot in functional data structures, is this concept of amortization, which is basically sometimes an operation might take longer than your expected 01 time, but if you can show that that happens a small enough percentage of the time to not affect the overall runtime, you can still say that the whole operation is 01. Even if, like, periodically, for example, we have to trigger that migrate, which will be a ON, like, reverse to the front. But you can show that that will only happen, like, every n elements, and then it takes n, so it effectively still ends up being 01. Because you can kind of, like, take each of like one cost per n sort of and like add it on and make that 2n. So this technique works. And so you can say that this actually is still an 01 data structure. However, there's a little wrinkle here. If you were to do this where you only enqueue and then dequeue kind of in a single code block, and you're not like copying the queue around, this holds. The problem is, imagine, we talked about the value of this persistence thing, where I can share the queue, and because it's immutable and persistent, it can be used here, it can be used here. Imagine I enqueued a bunch of items, and I share it right before, like there's only one element left in front, for example. There's a ton in the rear, and then I share that queue. And this queue over here calls tail, and this queue calls tail. Each one of them is paying that full reverse cost. So depending on the usage, this can actually, it's a fuzzy 01, I would say. You can really pay a penalty in a kind of a shared world. So one thing we can do is actually make this better by, rather than using lists to represent this, we can actually use streams. And actually, in fact, the rear doesn't even need to be a stream. The front only needs to be, but it just makes it a little more consistent. And I keep the lengths, and it ends up being a little better if, to prevent that like massive reverse dump that happens kind of at a given point, instead of waiting till the front is empty, we'll actually just wait until there are more elements in the rear than there are in the front, and then we'll trigger this migrate. Now the thing that really makes this better than the previous one is that memoization we talked about in the streams. So we'll end up returning, this f plus concatenated with the reverse of r. But if we were to share that, so we have these two streams that have r reverse in the back. But because of that memoization thing, if one usage of the queue forces that evaluation, and then another one uses it, it actually will be pre-computed. And so reverse will only actually be ran once, not for each time. Yeah?
Does that then interfere with the asynchronous thing, though, if they're shared somehow?
It doesn't actually. The worst case, it is, memoization is a little bit of a hack in a sense, but the worst case scenario is they get called at like exactly the same time, in which case the runtime might just run it for each one, but it should still always be consistent, and you still should never get race conditions. Like the value should be the same whether it ends up computing it or using the memoization, and usually it will be able to use the memoization. That's a good question though. Okay, so let's talk about trees. And I'm gonna motivate trees a little by a quote from Okasaki here, where he said, lists are the functional programmer's favorite data type. They're well supported by most, if not all, functional programming languages. However, one could argue that This support sometimes leads programmers to use lists when a more general sequence type would be more appropriate. I think this is definitely true. And it turns out a lot of those better data types end up looking a lot like trees. And we can talk about why. So I'm introducing this. Oh, sorry. What do we want in a better data structure? If we want some kind of general structure, ideally we'd like efficient operation of adding and removing from both ends, concatenation, insertion, and deletion at any point. Still want to be able to find things efficiently, and I want to be able to split this up. So if you think about doing a lot of those in a list, it's not great. So let's kind of start with the simplest tree. We have a binary search tree. I switched to Haskell for this. We could do all this in Scala too. It's just very succinct, and I wanted to mix it up. Kind of similar, this data declaration, for people who aren't familiar, that's kind of like the trait declaration in Scala, and then these are sort of the members of it. It's not a perfect one-to-one, but it's close enough. So a tree can either be empty, or it can be a node that has a left subtree, a element, or a right subtree. There are also other ways to represent this where the leaves also have a value. It doesn't really change it dramatically. And then insertion is fairly straightforward. If we have an empty list, we just return a node with that value. Otherwise, to use binary search trees, you have to assume that the things you're in have a sort, have an order. So if it's less than the head element, you'll move to the left. If it's greater, you'll move to the right, and essentially you just recurse. It's a recursive definition, so you'll do the same operation going down until you find a place to insert. So yeah, I have a little example there that just shows the result after inserting all that. And as we showed in lists, we can reuse substructures. So yes, we do have to make a new tree every time, but in this case, we're inserting E. And what ends up happening is every path we don't take, we actually can reuse fully. So in this case, we end up going to the right. The left path, as you can see in XS and YS, stays completely untouched. Our new node element just references that completely. We only have to kind of remake nodes on the path that we traverse. So this is kind of another hint to where we're going. To get really good performance in functional data structures, we don't want to go very deep, because the deeper we go, the more we have to build up as we come back up. But we'll get to that more. So binary search trees are okay. This simple implementation. The main problem in a functional version is that they only really work well if they're balanced, and it's hard to maintain balance on this definition. And if you don't, if you insert a sorted list, for example, you just end up basically creating a tree that goes basically as a list anyway. So you lose all your kind of log n properties unless you make sure that it's balanced. So people have worked out how to kind of balance as you build. There are actually quite a few. We're going to talk about 2-3 trees. There's also red-black trees. There's B trees. There's many. The idea in a 2-3 tree is that rather than having only one element in each and having a set 2 children always, we're going to be more flexible. We're going to say that a node can have 1 or 2 children, 1 or 2 values, and it can have 2 or 3 children. This complicates things, but it does improve. Sometimes when we get a new value, we don't necessarily have to remake children. We can actually just add it to our second value, for example. So this gives us a little more flexibility. It's just kind of laying this out again. Another thing we're going to try to hold in this form is that we're going to make all leaves be at the same level. And as in any search tree, we're going to keep it in sorted order. And this could be a representation of a 2-3 tree. This is not how you generally would actually see it. The problem with the representation is that if we have this property that all leaves are at the same level, this definition, if you were to like manually make a tree, you could break that invariant. You could easily make like a imbalanced tree. So this, you'd have to enforce that in the insert method, which you could do, but the types don't really help you. There are ways to construct this that the type system can actually try to help that. We can talk about it a little later. I'm not gonna walk through this because as these trees get more complicated, the insert gets more and more complicated, so I don't expect you to, we're not gonna walk through all these steps. This is just an example of like the different cases you have to deal with, and you make subnodes and have to do all these kind of tricky operations to build the new tree. But even though they're hard to get right, they're actually pretty efficient. With this 2-3 tree, we now get log n for everything. Search is still pretty easy. You have a couple more cases to deal with in your recursion, but it's just 2 nodes, 3 nodes kind of a thing. Now, one downside here is if you have to implement this, the insert is pretty complicated, and it's still not ideal. It's better, but like getting the min and the max is still going to be log n. Everything's sort of treated the same. So it turns out we can do better than this, and this is pretty recent. So there's a thing called the finger tree, and it was first explored by Leonidas Gubaz. I don't know if that's right. But the one we're going to be looking at is more recent. Ross Patterson and Ralph Hines wrote a paper in 2006, and these actually take 2-3 trees and modify them in a way I'll show you. So first, we're going to change the rules a little. We're now only going to store values at the leaves. And we're going to use a kind of funny, what's called a nested type representation, where so we still have this tree, but then node is actually different. And so the types for this end up getting really weird, actually. Basically, at your top level, your type of A is A, and then it becomes the second level, it's actually node of A, and then you actually end up with node of A. So every level, you actually get this like nested type. It's kind of weird to use in practice, but this definition actually ends up enforcing the like invariant that I was saying, where you end up only having things at the leaves. And then what we're going to do is we're going to take the nodes at the very end, and we're going to pull them up to the top. If you see, in this case, TH and EE, or REE, we've now kind of pulled up and let the rest drop. Why do we want to do this? I mean, and also, it's easy to see conceptually, it's a little harder in the code, but the reason is that now the front and the back of the tree are right at the kind of access point of the tree. So we now have O1 access to our front and our rear, and this structure kind of prioritizes things on the outside and then makes operations in the middle a little longer. So this is actually how it's represented. The implementations of insert and things are a little more complicated, but similar to that modified 2-3 tree, this is also a nested type. If you look at that deep constructor on finger tree, it has the same node from before, so it ends up having a funny irregular type. But it turns out, and actually showing the implementations of insert and everything on these, I'm not gonna, it ends up being quite hairy. If you want to see it, I recommend looking it up. But it turns out that by doing this, you actually can make a functional data structure that has O1 access to both ends. Random access is actually really efficient. You can still use it as a search tree. It makes a really good priority queue. Generally, the way it would be used is not directly, but someone would build a structure on top of it. And Haskell has a library called data.sequence that is a random access sequence that actually uses a very similar finger tree underneath to this one.
Is there an implementation of this in Scala?
Yes, there is. There's not one in the standard library, but people in the community have made quite a few. They're pretty interesting to look at. I know there was one in the, I think in the contrib libraries of Scala Z, they had one for a while. Just quick aside, the way that, so in Scala, the like sort of better random access functional structure is a vector. And the way it works is not a finger tree. It's actually a tree, but spelled funny, of it's 32 wide though. So basically it's a tree with a branching factor where each thing has 32 elements. So they say, in their docs, they say it's effectively constant, even though it's technically still logarithmic. But their reason for their claim is that you can only have 2 billion elements in a data structure in Scala. And with a branching factor of 32, or a log 32 of 2 billion is only 6. So they're like at most 6 operations, so they fudge it and kind of say it's effectively constant. It's still logarithmic, but anyways. Yeah, just kind of recapping. You may have noticed this pattern, but as those trees progressed, what happened is the top got wider, each level kind of got wider, and they got less deep. And the benefit of that is like you don't want to make it completely wide, because then you just end up with like a list. But some balance of that affects how much you have to rebuild when you make operations, and like how far you have to descend to get to things. So it turns out kind of tweaking your types and things to make it kind of almost square instead of like tree-like, it actually has a lot of benefits. So, all right. And last but not least, I'm going to talk about zippers. And a zipper, you might argue, is not really a data structure. It's a different way of looking at a data structure. And I will explain that a little more. So at its core, a zipper is basically a hole on a data structure that you can move around. Or you could also say a focus, for example. So if we want to make a zipper on a list, we end up having like a head list, a hole, and a rear list. Kind of give a little example here. And we actually maintain the list. In a way, this kind of feels a little like that queue implementation, but you actually maintain the list in the front of the list in reverse order. The middle is just an element, and the rear of the list is in normal order. The reason that's in reverse order in the front is that, let's say we wanted to move to the left. What happens is we just pop off the 3, so that's 01. 3 becomes the middle, and 4 just gets appended to the front of the rear. So those are all 01 operations. Similarly, if we want to move to the right, from this example, 4 gets prepended to the front of the front list. 5 becomes the middle, and we just leave 6 in the rear list. So any rotation is always just 01 operations. And yeah, as I said, they're basically you just kind of rotate through the lists. So move left kind of just moves everything that way, and move right, vice versa. And why would we want to do this? Well, it turns out now, with this focus, we can update basically for free. Since we just have the element we're on, we can make a new list zipper just replacing that one element. The lists don't change on the sides. And another thing you could do that I didn't implement here, but if you wanted to insert like another one to your left or right, so kind of sticking one next to your cursor, that's also cheap. You just throw it on whichever list you need. So when this might come up is, and we'll cover them more. These are more common with trees, but if you had a list, for example, where you had some kind of focal point and you wanted to make modifications around that point, this would be a much more efficient way to represent it than using a standard linked list. And you can always get your list out of this pretty cheaply. So yeah, this is, well, kind of explained this already. I'm just giving an example. I made a zipper kind of at the head, moved right 3 times, and then updated it to 0. And you can kind of see the effects of that. So you can also do zippers on trees. I think you can do zippers on probably all kinds of data structures. Rather than diving into code, though, I want to actually show how this is actually used in practice. There's a Scala JSON library called Circe that exposes a function or a data structure it calls an H cursor, which is essentially a zipper for extracting values and making modifications. And so over here we just define some JSON and we parse the document. And here's an example of using this H cursor. You see we have downfield of values, which is kind of descending the structure, and downfield of baz, and then we're like extracting that out as a double. Similarly here, we even descend into the quux array and move right to get B, which is the second element. Now, you may think, why bother with this instead of just representing this as like a map and grabbing the field each time? You can get better error handling, for one thing. If you try to do something illegal, it knows which access was the one that failed. The other thing this H cursor does, is actually why it has an H. It actually keeps the history the whole time you use it. So you can actually, after using this later, you could ask that H cursor to tell you like all the things you looked at. They also have an A cursor that's very similar that lets you do modifications. It's almost the same. It's just instead of as here, you'd like update it to a different value. You can imagine in like some big nasty JSON document where you want to functionally make a change 8 levels nested, or make a bunch of changes, for example. When you use it in this form, it kind of holds those changes and does them in a more efficient way than rebuilding the whole tree every time. And this, this isn't my MO, but apparently zippers are derivatives. Yeah, Connor McBride wrote a paper demonstrating that zippers, or one whole context as he refers to them, are the derivatives of their data type. Honestly, I don't really know what that means, but if that's interesting, Tony Morris is actually giving a full talk on zippers at 11 in the same room, and I know for a fact he's covering this. So if you want to really geek out on like, I don't know, category theory and things like that, I'm sure he can answer all your questions. All right, in conclusion, kind of just recapping, as programming becomes more and more functional and concurrent, purely functional data structures are becoming increasingly important. And it turns out with some cleverness, their performance can at least be within some margin of their imperative versions. And you get a lot of benefits in reasoning and reusability with immutable and persistence. So I hope this was a good overview. I have some time for questions, so I'm happy to answer any. Yeah.
A bit more concrete, or maybe raw moving pictures or something on that finger tree. That thing where you pulled things up.
Oh yeah.
It looked topologically identical to me, so I didn't get anything out of that. Where were we referring to? What chain?
I don't know if I can draw it. It's a fairly complicated structure. It's funny because in the papers, they often say that it's much simpler than what they were doing before, which is, you really, makes you know about the lives of academics when you're like, this is much simpler than what you were doing before. So.
That's the biggest thing. It's not topologically visible, the depth of various edges. Yeah, so look for that.
Let me show you the code though, and I can show you why it is different actually.
Go back to the other one.
Oh yeah. So if you look here, we kind of just make these nodes until we get to the end. If you look, I'll show you the code too that might make it more concrete.
Yeah, the T and the H and the RE, those two.
If you look at the actual code, you see these digits on the top? The difference is that rather than waiting till we get to the end of the tree, like in that 2-3 tree to have leaves that have values, we actually put values right at the top. So the very first instance of deep here has these digits which are some between 1 and 4 values. So they actually are accessible from the very first level of the tree, rather than descending all the way to the end to get those.
So
yeah.
maybe this will help me understand. If I have a pointer to this object,
Yes.
which of those little circles does it point at?
So if you had a pointer to the top of this, you would have a deep. And it would have 2 digits here and 3 digits here. And then this kind of spine, as they call it in the papers, is this sub part. The finger tree here is the spine.
So
So-
I can have multiple pointers into this thing?
Well, the top pointer would be one of these like deep instances.
In the graph, in this image though, this diagram, where is that?
It's sort of that. You'd like draw a box around this because it has this spine is kind of, you could actually kind of close it. It looks like 2 things, but it's not really. It's just because of the way we pulled up the drawing. It's sort of like this node right here.
Okay, that makes more sense.
Yeah, maybe.
Because without that unification of that top one, they'd just been dragged up from the bottom and there was no actual...
Right. No, you're right. This might not be an ideal.
The direction of the edges changed by pulling them up.
Yes. Yes, it did.
If you had arrows, there would be
That
Yes,
makes sense too.
that's true.
It's the 2-3 tree, you have the 2 nodes, right?
It is still the 2-3 tree that you've kind of like pulled up. Yeah.
Right, yeah. So you can't have that sort of double thing at the top.
Yeah.
Yeah.
Yeah. Yeah, I guess because a node is actually always 2 or 3 values. So if you work through the types or see like an example, it's pretty interesting. Very clever implementation for sure. Anything else?
Yeah, the finger tree didn't require the elements to be orderable, right? Or did it?
I don't think. I think it depends on what you want to do with the finger tree. Is the answer.
That's not a requirement of the structure the way it is with the regular.
I think it's not inherently a requirement. If you wanted to implement like a search structure on it, I think you would still want to enforce that. But I don't think it's necessarily the case. That's a good question.
So you have there, that compiles in Haskell.
Yes, it
That's
does.
totally fine. You can create this structure and use it, model as a finger tree, but you just might not be able to like actually find anything without iterating over every element.
Yeah.
You don't have any guarantee.
When you actually look at how they implement the methods, there's a lot more cleverness to how this thing is done. I didn't want to go too deep into this. It's pretty complicated. You could easily give a long talk just on finger trees. Anything else? Yeah.
Since we didn't go over insertion, this wasn't quite clear, but is there a large amount of garbage that's created as a side effect of mutating finger tree, or is it roughly about the same as a regular binary tree?
I think it's less.
That's
I think the way I would reason that out is you're basically going to create the amount of garbage as amount of new like nodes you make. And I think because this is sort of wide and it makes these digits and it has a lot of flexibility for not necessarily producing a whole new node, that the property that gets it in efficient insertion also means it doesn't generate too much garbage. Yeah,
So I have one other really basic question.
no problem.
When you talk about queue,
Yeah,
it's an immutable queue.
yes.
To me, a queue is a mechanism for communicating between 2 threads in
Yes, so
other systems. So I still have the problem that I have to communicate the mutated, the new representation
right,
across to the other thread.
right.
Okay, good enough. I'm
This,
okay with that unless
yeah.
people want to hear how you're proposing to
I
do
think
that.
usually like a queue for threading is a little different use case of a queue than the kind of like pull things from the front of the list kind of queue.
Yeah, that's
But
kind
yeah.
of what I was getting at with my question.
Oh, okay, yeah. I think this is not the right queue for that. I think they have a different queue that you use for different threads and processes. Yeah, right. Yeah.
Can you comment a little bit more on Scala's vector versus the finger tree? And
Sure.
when you might use one or the other?
Yeah. I'm curious. I haven't benchmarked the finger tree implementations that people in the community have done. I mean, they look like they're well done. I didn't even see benchmarks there. In the finger tree, these operations like the min and the max and things like that are actually O1, but I don't know what the constant factor is. The vector in Scala They like to throw that EC, if you look at their docs, effectively constant, but it really is like a logarithm, like log 32 of n. That said, if log 32 can only be 6, the constant factor could easily make the finger tree slower, potentially. I don't actually know what's the case in practice. Like, I haven't benchmarked these, so I'd be curious to see if like you did get better performance out of a finger tree in Scala than you. And we could do it. I didn't do it for this. So I wonder. I mean, maybe in the future this will be. Maybe they will adopt one of these, and it could become the general structure. So.
My impression has been that the try, when all is said is done, it performs much better.
Yeah.
I know.
That could be.
It has a
Yeah.
data structure like that, and it sounds like it performs really well.
Yeah, I mean, in theory, if we were talking about, 100 billion elements, which we can't make, but at some point this would certainly start performing better, but maybe at realistic levels it doesn't actually. Maybe it's a little too clever for its own good, perhaps. Yeah.
I was curious with the whole idea for being purely functional data structures.
Yes.
Do you have Scala or Haskell and GHD? Do either one of them actually implement purely functional data structures? Because you don't have guarantees that your data structure won't be mutated at the machine code level, at least in Haskell. It can do all those optimizations for you because it can reason about your code.
Sure.
So it will not mutate, not force garbage collection when it doesn't need to.
Yes. I think at this we're kind of speaking at the conceptual level. Okay. What happens underneath is sort of there be dragons, I mean, often even like maps and things get turned into while loops, and like at assembly it's all mutation, right? So.
That's what I was
Oh, okay.
I mean, some of the things we're talking about at the conceptual level are this should be less efficient if you were actually copying the entire data structure.
Right.
But when you compile it and you turn on O3,
yes.
it doesn't do that. So why does it matter?
Yeah, it kind of depends on the runtime and things like that. You're definitely right that sometimes the runtime can take something that should have certain properties and do better or worse. I think Haskell's compiler and runtime definitely is better for these things. It's better at not creating lots of like doing things like stream fusion and things. But that's a little I don't know. It's a good question, but it's a little deeper than I know. Yeah. Anything else? All right. Well, we're out of time. If you want.